Well, to be specific, the focus is going to be on the lookup table evaluation in a homomorphic context. This is work by me, Aysecan Abidin, and Bart Preneel. First, however, we'll need to introduce some background on homomorphic encryption, which some people may already be familiar with. Okay, so the gist of FHE here, I think most people know. Now you usually have your normal encryption scheme. You can encrypt, decrypt. With FHE, you have more procedures that will allow you to do arbitrary computation on this data. One such example is you may have procedures that will allow you to add or multiply ciphertexts, yielding the sum or product of the encrypted values. One flagship application is privacy-preserving machine learning. You could encrypt your medical data and send it to some provider who will analyze it without ever needing to see it. Very loosely speaking, there are two groups of FHE schemes: the single instruction multiple data type schemes like BGV, BFE, CKS. They usually perform polynomial operations on vectors of data. On the other hand, we have accumulator-based schemes like TFHE or its predecessor FHEW. Unlike the SIMD schemes, they will tend to encrypt smaller values, but they will be able to encode lookup tables into a special procedure, which we'll see later. So we can easily truly perform arbitrary computation here. And as you may have guessed, this talk will focus on the latter. So what's the setting? I'll show you first how would I encrypt values in this context. So the ciphertexts are so-called learning with error samples. The key would be secret vector from the integers modulo q, and we'd have some message space between 0 and t excluded. To encrypt, well, what we do is we would first sample some random vector from the same space as the key and compute the inner product, add the message, add some small error, which is usually sampled from a discrete Gaussian distribution. And to decrypt, we would, again, take this right-hand side, subtract the inner product of the vector and a secret key, and we get m plus the error. The only issue is that, well, if we just have m plus the error, we might not be able to actually recover m. So what people tend to do is just scale the message such that the message bits and error bits are separate, and we can just recover the message by rounding to the closest multiple of q over t. Okay, we can play a similar game when we want to encrypt polynomials. In this case, the secret key is going to be a polynomial from this ring up here. So note that n is the power of 2. This instance, ciphertext would be called ring learning with error samples. Encryption mostly works the same. Instead of now, we have a random polynomial. And decryption, likewise, we compute the subtraction of the right-hand side, so this term here, the product of the random polynomial and the secret polynomial, and we'd end up with this term over here, and we can again round to obtain the message. All right, then maybe some properties that will be useful in general. Both LWE and ring LWE are additively homomorphic by default by just adding their respective components. This is kind of written here, and then it's fairly easy to see that by adding the ring LWE samples, we get a ring LWE sample of the sum. This will also mean that we'll have a homomorphic property with regards to scalar multiplication. In the case of LWE, it means we can multiply by some integer. And for ring LWE, we can multiply by polynomials and obtain an encryption of the message times polynomial. Now, the last property, which is very useful, is that if you have n LWE samples of some values here, we can combine them into a single ring LWE sample encoding a polynomial whose coefficients will be equal to these messages. And going the other way around, so if we have a ring LWE of a polynomial, we can produce LWE sample encoding each coefficient. And the latter is much more efficient, but that's not too important. Now, the cooperation that all accumulator-based FHE schemes use is called blind rotation. I won't show the steps because there's different ways to do it. But the gist is the blind rotation procedure takes two inputs. The first one is a polynomial or a ring LWE sample encoding a polynomial and some ciphertext. And it's going to output a ring LWE sample of this polynomial times the monomial, to the power of the decryption of the ciphertext. Now, this is a bit abstract, so maybe let's look at a specific example. So if we set our ciphertext modulus equal to n, so yeah, this n up here, then if you fully write out without the modulus reduction, the decryption, and plug it in, what we'll see is, well, indeed, we have this polynomial times the monomial to the power of decryption, but we also have a random sign flip. And this is something I mentioned, or rather I showed earlier, is that in the ring we're working with, x to the n is going to be congruent to -1. So if we take this whole thing modulo 2n, well, either kn is even, in which case this whole term can be divided by 2n, so there's no sign flip. But sometimes it's, well, just going to be odd, so we'll have a random sign flip that's near unpredictable. Okay? And the second interesting case is when the modulus is equal to 2n. We can, again, write out the entire decryption here. And if we plug that in back to a definition, again, we'll have a sign flip multiplied by a monomial. The only difference here is that this sign flip will depend on the most significant bit of the decryption of the ciphertext, whereas the power of this monomial is just going to be the encrypted ciphertext modulo n. All right, this is a bit abstract. It will be illustrated a bit more later. All right, let's come to homomorphic lookup table evaluation. Well, the setting for lookup tables is one you'll be familiar with. So we can view a lookup table just as a multidimensional array, and we give in a set of indices or digits we'll use to index into this array to obtain some value. The difference is, in the encrypted context, the indices are, well, also going to be encrypted. So the question is, how do we actually evaluate this thing? So the easiest case is if we have a single digit that's relatively small. And the intuition behind it is going to be that using the blind rotation procedure, we'll just rotate the coefficients of a polynomial, and the polynomial is going to encode the values of the lookup table. So for example, the constant coefficient would correspond to the lookup table value for an input 0, and well, continuing with that, then slot 1 is going to correspond to the lookup table value for an input of 1, etc. And this is also outlined here with the actual steps. The only thing we'll need to pay attention to is this requirement here, because if we don't make sure that the most significant bit of the decryption is 0, as I've mentioned earlier, we'll have a sign flip, which we do not want. And then, well, the output is going to be this ring LW sample ACK. And I mentioned at the very beginning, we can extract an LW sample from the coefficients of the polynomial within it. So this is how we can evaluate such a lookup table. If you want to circumvent this most significant bit requirement, there are methods to do so. I've included them here and fully at the end. So if you want to learn more, you can check that out. The more interesting case now is if you have multiple digits to index a lookup table. The primary work, there's one primary work, this one up here by Guillamares et al. And I won't explain it in detail, but rather illustrate it through an example. So just for the sake of argument, assume we have 2 digits, just 2 digits, and we'll just view the lookup table as a matrix with, well, for example, L00 is the value we'd get for an input equal to 0 and 0. So what we can do now is basically we'll apply the method for the single digit case to every row. So we'll encode the rows of this matrix into ring LW samples and apply the blind rotation, and this is also illustrated here. So basically what will happen is that the 0 column will then consist of the rotated values. So this is then fully dependent on the first index. So what we can do is extract these constant coefficients of the resulting ring LW samples and pack them again into a single ring LW sample. And then the second stage is, well, we take this new ring LW sample, apply the blind rotation with regards to the first index, and the constant coefficient of that will be indeed L at index 0, index 1. If this was a bit too abstract, you can just think of it as we have a matrix encoding the lookup table. First, we rotate the columns by the second index, and then rotate the rows by the first index, and then the 0, 0 slot contains our desired value. All right, this method is nice and quite elegant, but it has some problems. For one, without additional modifications, it's fairly easy to see that the amount of blind rotations will be exponential in the number of digits. And since this blind rotation operation is the bottleneck in these schemes, it will mean it's going to be extremely slow. Another issue is that, well, we need to repeat this procedure for every output digit. So again, this will cause things to be slower. And this most significant requirement is also somewhat awkward or bothersome. Just for the sake of completeness, at least the first problem can be solved by doing something called circuit bootstrapping, which will transform LDV samples into a different type of ciphertext, which we can just multiply with polynomials without needing to do any blind rotations. All right, now we can actually come to the contribution. We'll focus on a very specific setting. First, we'll assume that we have U digits and in base 2. So we're working with bits, which is, well, quite common when we're working with binary circuits. One example, also mentioned in the last talk, is when we want to homomorphically compute the AES box. And we'll also have that we'll have an input of U bits as well. We want to obtain all digits at once, and obviously we want to minimize the number of blind rotation applications we'll need. So the first ingredient we'll use is, well, kind of an observation. So assume we'll have a set of lookup tables mapping from some space to bits. And obviously we can again encode these lookup tables into polynomials. What we can do first is we set this rotation polynomial for blind rotate to 1, use a modulus equal to n this time, do the blind rotation, and from this accumulator we just start multiplying with our lookup table polynomials. And as I've shown a few times before, then the constant term will fully depend on the encoded index. What about sign flips here? Because I mentioned them a few times, there were problems, so why not here? Well, because, well, if q is even, then q half is going to be equal to minus q half mod q. If q is odd, then it's just going to be off by 1. Since we later on round anyways, we can effectively ignore this. And with this, we can already outline the first part of the lookup table evaluation procedure. So the first part is, and this is not something I'll show because it's simple but not particularly interesting, we can use blind rotation to combine a set of omega bits into a single integer represented by those bits. So if you have LDV samples encoding 1, 0, 0, we'd get an LDV sample of 8 in the first step. Then we'll have U minus omega bits left, which haven't been used yet. So what we'll do, we're just going to assume certain values for those bits, and using the previous slide, we'll generate all possible outputs, independently of whether the chosen bits are true or not. And again, this will just need one blind rotation, this step 2. And then, this is again something mentioned at the very beginning, we will pack the groups of LDV samples into different ring LDV samples based on the bit values we assumed. So for example, if for the last bit we assumed 0 for one polynomial, and for a second polynomial we assumed 1, we might pack them into different ring LDV samples, like the output bits. We can pack them into different ring LDV samples. And then, well, our correct output will be in one of those ring LDV samples or in some chunk of a ring LDV sample. So the question is, how are we going to select the correct one? And this will turn out to be fairly easy, and we'll rely on a relatively simple identity. Say we're working over some field. So we want to pick between two values v0 and v1, and we have this selector value, which isn't going to be 0, 1, but rather a sign. And then it's fairly easy to see, well, if the sign is 1, if we apply this formula, we get the first value, otherwise the second one. And then based on this, you may already guess what we're about to do. Well, first recall that if the modulus is equal to 2 times n, and we write out the decrypted index, again, since we're working with bits, this t you saw earlier would be 2. Well, if you write this out, then you'll see, well, the most significant bit will fully be dependent on index I. Here I wrote that it's equal to index I, but this is just based on the assumption that E is positive, because if it's not, we can make it by shifting it slightly. So this most significant bit is fully characterized by the encrypted bit or encrypted index. So to actually choose between two ring LDV samples, what we can do is, well, we're going to add them, blind rotate the difference, which will induce this sign flip here. And the result will be approximately the ring LB sample corresponding to our bit. Though in practice, the lookup tables dimensions we'll look at will be so small that the second ring LB sample is most likely going to be a rotation of the first one because we have so much space to put our values into. Right? And this then gives already the full algorithm. So first we generate all outputs, pack them into ring LB samples, and then for every remaining bit, we iterate the previous mux until we get the correct output. Now, what are the theoretical advantages of this? Well, the first two steps only need to be applied once. No matter how many LUTs you have, you'll just multiply by more polynomials. Now, for U less than 10, it's fairly easy to find parameters where we'll only need as many blind rotations as there are bits. Compare this to the naive application of this paper, which is going to be exponential, or even a modified one where we'll have a multiple of U. This is already much better. And a nice advantage is the first stage where we compose the bits can be parallelized, so effectively we'll only do U minus omega blind rotate calls. Though for completeness, if we have a huge number of bits, we'll still most likely need to do an exponential amount of blind rotations. Okay, in practice, what are the results? We'll apply this to Transciphering. So if you remember at the very beginning, I said that with FHE you can compute arbitrary functions, arbitrary circuits. So it means if we are given the bits of a block of an AES application, we can run the decryption circuit on those values homomorphically, given an encryption of the round keys, to obtain encryption under FHE. This is what we'll test this algorithm on. Specifically, we'll use the lookup table algorithm to evaluate the S-box. And compared to other papers, the speedup is anywhere from 1.5 times to 4 times faster. Now, in absolute terms, depending on the failure rate, this is characterized by the parameters, it's going to be 81 or 112 seconds, which, well, compared to the clear text is still gigantic, but already much better. Right, here's a summary. You have a new homomorphic lookup table evaluation for binary digits, where we get all digits at once, and which is, I would say, much faster than other recent works. So thank you for your attention. And if you're interested in the references, here they are.